Welcome back, Physics 30. This is the last in the CO2 section. The other video we looked at elastic collisions when kinetic energy is conserved. The total kinetic energy before equals total kinetic energy after. But now we're going to look at inelastic collision, in which kinetic energy before does not equal the kinetic energy after, because some is transferred into heat and other types of energy. So we'll apply the law of conservation of momentum and energy to solve problems involving an inelastic. Explain what is meant by inelastic. So collisions in which kinetic energy is not conserved is called an inelastic collision. So some of the initial kinetic energy is transformed into other types of energy, such as thermal energy, potential energy, so that the total kinetic energy after is going to be less than it was before. The inverse can also happen when potential energy such as chemical or nuclear energy is released, in which case the total kinetic energy after will be greater than initially because some came from that stored energy. Explosions are examples of that type. Typical macroscopic collisions are inelastic, as I mentioned in the last video. So most of the time we do have inelastic. The only time you actually have elastic is with ideal gas molecules in a certain scenario, a container in which we're not having kinetic energy change into some other form. But of course, we sometimes make an assumption that something is close to being elastic, therefore we can make the assumptions we did in the previous video. But if we look at what usually happens in real life, if we look at two objects sticking together as a result of a collision, we would say that it's perfectly inelastic. Two colliding balls of putty that stick together, or two railroad cars that couple together, are going to be examples of completely inelastic collisions. The kinetic energy in some cases is all transformed into other forms of energy in an elastic, but in some cases only part of it is. Now, we looked at an earlier example in a few videos ago dealing with two train cars coming together and sticking together. We're going to look at that again. In a completely inelastic collision, the maximum amount of kinetic energy is transformed to other forms consistent with conservation of momentum. Even though kinetic energy is not conserved in elastic, again, the total energy is conserved. It's just that the energy changes form from kinetic to thermal or something else. And of course, the momentum is always conserved with any collision as well. So if we look at the railroad car example that we had, so for a completely inelastic collision of two railroad cars that we just considered earlier, calculate how much initial kinetic energy is transformed to thermal or other forms of energy. So recall that they were two 10,000 kg cars. We had A traveling at 24 meters per second and B was at rest, and then they locked together. And we looked at conservation of momentum with that one, and we looked at what the velocity was after. So on the next page, if you recall, this was the scenario that we had, and then we calculated V prime, because they both travel at the same velocity, so there's no need to separate it into a VA prime and VB prime. I just called it V prime, and I think we calculated it to be 12 meters per second. Okay, so that's what we had. So using conservation momentum, we were able to figure that out. Now let's look at kinetic energy. Kinetic energy comparison. So let's look at it before collision and after collision. So before the collision, mass of A multiplied by the velocity of A squared plus 1/2 mBVB squared. And then of course after, we use mass of A, except the velocity of A after. Now of course VA prime and VB prime will still be 12, so I could put in just M prime here, it doesn't matter. But earlier we knew that since they stick together, these velocities are going to be the same. So there's no need to distinguish between A and B because it's just simply V after. But that's okay. We'll just treat it like this. So 10,000 kgs. A, we were told, was going 24. and B was not moving. So BEDMAS brackets, exponents come first, then multiply, so 24 squared, then times 1,000, then times a half. We get 2,880,000, and of course this part here is going to be 0. Now if you look at what happens after, so 10,000, now they're moving together at 12. Oops. And B is moving at 12. Of course, we're going to square that. 720,000. 720,000. So, of course, yes, we see 1,440,000 joules. So if we compare these, we see that there is a loss. So difference, total energy we had at the start, 2,880,000. Subtract what my final kinetic energy is going to give me, well, it's just 1,440,000. And I can say this energy has become thermal and other forms of energy. So I hate to use the word lost. It loses kinetic energy, but what's really happening is that kinetic energy is being transformed into something else. So conservation of momentum always happens, but conservation of kinetic energy doesn't. If it's a perfectly elastic collision, these two numbers would be equal. But because it's an inelastic collision, we have an energy transformation. Some of that kinetic energy is transformed into something else. All right, so you should be able to do the assignment. And again, that's the last section here. So we'll see you again.